So we looked at the invertible matrix theorem. We said there were 10 different equivalent statements. So we had A as invertible was equivalent to 9 different things, and we want to make use of that to determine if a matrix A is invertible or singular. And we want to use as little work as possible. We want to use the least number of computations to do that. So number one, I'm going to start with a matrix A. Ask, is it invertible? So my matrix here is going to be, let's see, 2, 7 in the first column, 3, and 8 in the second column. So all I'm going to do, I'm going to row reduce that just to a point where I have it in echelon form. And if we have a pivot in every row or we have a pivot in every column, it doesn't matter, right? There are 2 rows and 2 columns, so you have the same number of rows as columns. So if you have a pivot in each row, pivot in each column, then you can guarantee invertibility. Remember, that was one of our big results. A is invertible if and only if A is row equivalent to the identity, or A is invertible if and only if it has exactly n pivots. In this case, 2 pivots, right? Because you have a 2 by 2 matrix. So let's just do a basic echelon reduction. So what I'm going to take 7 times row 1 plus -2 times row 2 to get a new row 2. And this big squiggly mark is not looking at, there we go. Okay, so row 1's not going to change. We're still going to have 2, 3. But what I'm going to do, I'm going to multiply row 1 by 7. I'm going to get 14 and 21, right? And we're going to add that to row 2, which is multiplied by -2. So we're going to have -14 and -16. Add them together, you get what? 0, 5. It's going to be my new second row. So I've put that in echelon form. Notice you have 2 pivots, right? So as soon as you see you have 2 pivots, since this 2 by 2 matrix A has 2 pivots, then we know it's invertible. If it had less than 2 pivots, it would be singular. But because it has the full number of pivots, it's invertible. Since A has 2 pivots, then A is invertible. So as little work as possible, that's the idea. Number 2. So we have a matrix A that's 4 by 4. Let's say it's 1, 2, 3, 4 in the first column, 5, 6, 7, 8 in the second column, 0, 0, 0, 0 in the third column, and 9, 10, 11, 12 in the fourth column. So with as little work possible, what can we say? We don't even have to do a row reduction or anything here. We can just immediately notice that you have the 0 vector, right? So even though we haven't put that in echelon form, we know there's going to be a column without a pivot. That's one way to do it. Or another way is to say that the columns of A are linearly dependent. Remember, anytime you have the 0 vector, the columns of A are linearly independent. So let's say note, since the 0 vector is contained in the following set of vectors: 1, 2, 3, 4, 5, 6, 7, 8, 0, 0, 0, 0, 9, 10, 11, 12. So note that since the 0 vector is contained in this set of vectors, then this set of vectors, 1, 2, 3, 4, 5, 6, 7, 8, 0, 0, 0, 0, 9, 10, 11, 12. That set of vectors is linearly dependent. Oops. Didn't turn out well. There we go. So since the zero vectors contained in this set, then this set is linearly dependent. Now, what does that mean? If the set of vectors is linearly dependent, well, remember, A is invertible if and only if the columns of A are linearly independent. So if the columns of A are linearly dependent, that means A is singular rather than invertible. So thus, A is singular. Okay. So you really didn't have to do any work. Just notice the zero vectors there in the column. Number 3. Let's say I were to have something like A equals a 3 by 3 matrix. 5, 4, 3 across the first row. 0, 1, 2 across the second row. And 0, 0, 0 across the last row. The third row has 3 zeros. What can we say about this? Well, if you pay attention, the first row has a pivot, the second row has a pivot, but the third row doesn't have any pivots, right? So because you have a row of zeros, you're guaranteed you won't have a pivot in that third row. So note row 3 has no pivot since A has less than 3 pivots, it will be singular. Remember, in order to be invertible, you would need 3 pivots, and you're never going to have 3 pivots with the row of zeros down there in the bottom, because there's no pivot down there. Okay, what else? 4. Let's say I have a matrix A. 1, 5, 9, 11 in the first row. It's going to be a 4 by 4. Second row, let's say we have 0, 2, 5, 8. The third row we have 0, 0, 4, 6. And the last row we have 0, 0, 0, minus 10. So what can we say about this matrix? I don't like my parentheses here, my soft brackets. Can we say this is invertible? Definitely, right? You got 4 pivots. 1, 2, 3, 4. You have a pivot in every row, every column. So this is invertible. A is invertible since it has 4 pivots. It's a 4 by 4 matrix and it's 4 pivots, so it's invertible. Okay, here's a little exercise we're going to do. Before we do this exercise, let's give a definition. What's a upper triangular matrix? Definition. An n by n matrix, it's a square matrix, is upper triangular provided the entries below the main diagonal are 0 entries. Below the, let's call the main diagonal the descending diagonal are only 0 entries. So what does that mean? If I were to write A like this, in entry form we'd have what? A11, A12, dot, 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 A1n. That would be the first row. Now, A11 is on the descending diagonal, so I'm going to have zeros below that. I'm going to have 0, 0, dot, 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 zeros. So in the second row, it starts with 0, then it has A22, and then it would have like A23, and A24, and then A2n. Now A22 right there is on the main diagonal, the descending diagonal, so we're going to have a 0 below that and a bunch of zeros. All right, and so on and so forth. So you're going to be going down this diagonal, and you're going to have all the way A33, A44, all the way to A and N. Now below this diagonal, you're going to have a bunch of zeros. So if you imagine being upper triangular, and that means this right here forms kind of like a triangle. And in the bottom left corner, you have your zeros. Now A11 could be 0, A22 could be 0, A12 could be 0. Those could be zeros, those A's could be zeros, but they're not required to be. They could be anything they want it to be. Just have to ensure that anything below the main diagonal is 0. Okay, so here's a question, exercise. When is an upper triangular matrix invertible? Invertible. So if you look at this upper triangular matrix here, when is this invertible? So keep in mind that matrices are invertible precisely when they have exactly n pivots. So a pivot in every row, a pivot in every column. So that, oh crap, I lost something. Let me go back and, come on now. That means that you need a pivot here in the first row, the first column. You need a pivot here in the second row, second column. You need a pivot all the way down the diagonal, right, to guarantee you have n pivots, right? A11, A22, all the way through A and N. So that means these cannot be 0. So when is an upper triangular matrix invertible? When its diagonal entries are non-zero. Or another way of saying that is A11 is not 0, A22 is not 0, A33 is not 0, and so on, dot, dot, dot. A and N is not 0. The diagonal entries are non-zero. Important. Okay, let's just do another quick exercise. Show that if AB is invertible, then A is invertible. This is basically a proof, right? If AB is invertible, then A is invertible. So you're proving an if-then statement. So I'm going to write a little proof here. Anytime you're proving an if-then statement, you're going to assume this part here in blue after the if, and you want to arrive at this part here after the then. So we're going to assume that AB is invertible. So let's suppose AB is invertible. What does that mean? We can use one of our characterizations of invertibility. One of our characterizations of invertibility is that there exists a matrix, you can call it whatever you want, such that AB times that matrix gives you the identity. Let's call that matrix D. Then there is, or there exists, a matrix D such that AB times that matrix D gives us the identity matrix, right? Now the definition of invertibility is there is a matrix D such that AB times D equals identity and D times AB equals identity. But if you remember back here, you only have to do it on one side. Okay, that was in our invertible matrix theorem, so I don't have it written down here. That was number 9 under the invertible matrix theorem. You only have to be able to multiply from the right side. Multiply your invertible matrix from the right to get the identity, and that's what I'm doing. I'm multiplying from the right. AB times D, so D is coming from the right there. Okay, green. Now what I'm going to do, I'm going to reassociate the parentheses. So what do we have? We have A parentheses B D gives you the identity matrix. So now notice we have A times the matrix to get the identity, right? A times the matrix, BD gives you the identity. So if A times the matrix gives you the identity, then by using that number 9 once again, you can say, therefore, A is invertible, right? Why can you say A is invertible? Well, according to 9 in the invertible matrix theorem, if you can multiply A by something coming from the right and get the identity, then that means A is invertible. So that's it. That is it. A is invertible. That's what I wanted to prove. All right, so I think it's that. This